Continuing our coverage of the mechanics of capital budgeting, we look at three remaining metrics and their usage: modified internal rate of return, regular payback, and discounted payback. Here are the two sample projects we're using to demonstrate the various methods. Remember, we said that NPV dominates even if the result conflicts with another method. Let's explore how those conflicts can occur. Still using our two sample projects, L and S. The table shows the NPVs for both projects at varying cost of capital values. At low rates, Project L dominates. At higher rates, Project S dominates. The crossover rate is the discount rate where the NPV of the two cash flow streams are the same. To find the crossover rate, we'll use the change in cash flow column on an early slide and repeat it here. In this example, we subtracted S's cash flows from L's, but it doesn't matter which way you subtract. Enter these cash flows in the CF worksheet and solve for internal rate of return. The result is the crossover rate. If an arrow displays, the profiles don't cross, so there will be no conflict. Our crossover rate is 8.7%. If the cost of capital is less than 8.7, there'll be a conflict between IRR and NPV. If the cost of capital is greater than 8.7, no conflict. What makes the profiles cross? Size or scale differences, one project involving significantly larger cash flows than the other, or timing differences. That's the case with our two projects. One generates large cash flows sooner. Comparing NPV and IRR. If the projects are independent, NPV and IRR always lead to the same accept-reject decision. If the projects are mutually exclusive, that's where the conflict can happen. As we just showed, if the cost of capital is greater than the crossover rate, no conflict. If it's less, you're going to have conflicting decisions. Let's look at the problems with internal rate of return mentioned in Part A. The IRR methodology has two serious issues: the reinvestment rate assumption and multiple IRRs when you have non-normal cash flows. NPV assumes reinvestment of inflows at the cost of capital, while IRR assumes reinvestment at the internal rate of return. This means if the internal rate of return is 25%, inflows are reinvested at 25%, which probably overstates the internal rate of return. Reinvestment at the cost of capital, a market rate, is more realistic. NPV should always be used to choose between mutually exclusive projects. In solving for internal rate of return, we're solving for the root of an n-degree polynomial. Descartes' rule of signs says that there will be one real root for each sign change, with the remaining roots imaginary. For a project with non-normal cash flows, that means for each sign change, you can get a real solution to internal rate of return. A solution to both the reinvestment assumption and the multiple IRR issue is to use the modified internal rate of return. The formal definition is on this slide, but it'll be more useful to see the chart. As the slide states, modified internal rate of return actually allows reinvestment at the opportunity cost. It also avoids the multiple internal rate of return problem. Since managers like a rate of return for comparisons, MIRR is better. Using Project L as our example, our first step is to find the future value of all inflows, all positive cash flows. Note that TI Business Analyst 2 does not solve for the future value of an uneven cash flow stream, but it's easy to find it in your calculator, which is covered in the MIRR video tutorial. In this example, cash flow 1 of $10 is future valued 2 years. It's equal to 10 times 1.10 squared. The $60 is future valued 1 year, and $80 is already at the end of the timeline. These are added together to find the terminal value. We need to find the discount rate that will grow the $100 outflow at time 0 to the terminal value of inflows of 158.1. You can solve this with the TVM keys, as we'll see on the next slide. Enter the values in the TVM keys. N is equal to 3, present value is a negative 100, payment is 0, future value is your terminal value, 158.1, compute IY, 16.5. In Excel, you can use the rate function. Excel also has a dedicated MIRR function. Note that the Excel MIRR function asks for 2 rates. The finance rate is the discount rate applied to outflows. Since we only had one outflow, this wasn't used. The reinvestment rate is the future value rate. And for our problems, we'll use the weighted average cost of capital for both rates. As an example of multiple internal rates of return, suppose we have the Pavilion project. At time 0, we need to invest $800,000 to build a World's Fair pavilion. During the fair, we estimate we'll make $5 million, but it will cost us $5 million to put the land back like it was when the fair closes. These values are shown on the timeline with a cost of capital of 10%. Solving for NPV, we get a negative $386,780. But IRR results in an error, 2 sign changes. Here's a look at the results of our Pavilion project. At very low discount rates, the present value of cash flow 2 is large and negative, so the NPV is negative. At very high discount rates, the present value of both cash flow 1 and 2 are low, so CF0 dominates. Again, NPV is negative. In between, the discount rate hits CF2 harder than CF1, so the NPV is positive. Result, 2 IRRs, 25% and 400%. 25% is possible. 400% is clearly not. Now that we see how MIRR works, let's revisit our Pavilion project as it illustrates an important point about finding the values to use to find MIRR. All outflows are present valued to time 0 and summed to use as the present value. Outflows to the left on the timeline. All inflows are future valued and summed to use as the future value. Inflows to the right on the timeline. With the Pavilion project, we have 2 outflows at time 0 and time 2. So the cash flow at time 2 must be discounted back to time 0 and added to cash flow 0. Negative $5 million divided by 1.10 squared is equal to a negative $4,132,231.40. Adding the initial $800,000 outflow results in a present value of a negative $4,932,231.40. Future valuing the $5 million at time 1 equals $5.5 million. N is 2. Present value negative $4,932,231.40. Payment 0. Future value $5.5 million. Compute IY 5.6. Anytime you have more than one sign change, use MIRR. For our Pavilion project with an NPV of a negative 386.78 and an MIRR of 5.6% versus a cost of capital of 10%, this looks like a no-go. This would be an opportunity to consider that the firm may well decide to go ahead with the Pavilion anyway, knowing that they'll lose almost $400,000. They may decide it's worth it for strategic reasons. Do you think McDonald's going into China was a positive NPV project? Probably not, but they went anyway for the strategic advantage. If MIRR still sounds a bit confusing, watch this video tutorial which walks through MIRR step by step. Our last 2 methodologies are payback and discounted payback. Payback is the number of years to recover the project's initial cost. It's one of the easiest to understand metrics, and we'll walk through an example. Using Project L again. Accumulate the cash flows from time 0 to the last year. We're looking for when the sign of the accumulated cash flows changes from negative to positive. For Project L, the sign change occurs between years 2 and 3. A fundamental assumption in finance is that cash flows occur at the end of each period. But in this case, we assume they are evenly spread throughout the year. So we want to know how far past year 2 toward year 3 we have to go to exactly pay back our initial investment. The logic in this example is that at the end of year 2, you were still short $30. But by the end of year 3, we earned another $80. So how far into the year did we have to go to cover the $30? We find the fraction by dividing the last negative cumulative cash flow by the cash flow in the next year and taking the absolute value. In this case, that's the absolute value of a negative 30 divided by 80, which is equal to 0.375. Add that to the last year with a negative cumulative cash flow, and you have the payback, 2.375. Repeating the process for Project S results in a payback of 1.6 years. One major problem with payback is that it ignores the time value of money. Discounted payback solves that issue. The technique is the same, except the cash flows are discounted before they're accumulated. 2 things to note. The discounted payback will be longer than payback. The sum of the discounted cash flows will always equal NPV. Both paybacks do give an indication of risk and liquidity, which may be critical to smaller firms. Payback is easy to calculate and understand. It's almost a back-of-the-envelope metric. However, Regular payback ignores the time value of money. Both paybacks ignore cash flows after the payback period, which biases the result toward projects with larger cash flows earlier on. The main problem is that it asks the wrong question. We're looking for projects that will increase the value of the firm. Payback measures when we'll get our investment back. Discounted payback does use the time value of money, but the other issues still exist. This video tutorial covers NPV, IRR, payback, and discounted payback. In summary, with today's computing power, it's easy to calculate all the metrics. While NPV is the dominant one, each does provide some valuable information. NPV is a dollar value and indicates the expected increase in the value of the firm. IRR is a percentage and gives an indication of risk. MIRR is a percentage and corrects problems with IRR. Payback and discounted payback are in years and indicate liquidity. This ends our coverage of capital budgeting methodologies.